AP Chemistry, Unit 2.2, Intramolecular Force and Potential Energy. Chemical bonds are, again, the attraction between the nucleus of one atom and the electron of another. And the balance between my attraction between the protons and electrons and the repulsions between electron-electron and proton-proton must be met. I need to balance the attraction and repulsive forces there. So we're going to look at a potential energy curve for a covalent compound. And we're going to see 4 different regions here. So on my y-axis, where we have the x-axis marked as my my distance, my y-axis is my potential energy, and our intercept here is going to differentiate between an unstable bond and a stable bond. And then I have 4 regions here that are color coordinated with the notes that reflect what's going on in each of those regions. So first up, I go ahead and talk about this red situation here where we have quite a large distance between my molecules. I'm not going to have any attractive or repulsive forces between these molecules. My potential energy is going to be at 0. Then as we have the atoms moving closer together, we are starting to have some attraction between the atoms, the nuclei, and the valence electrons, and there's going to be very limited repulsion, and my potential energy is decreasing. At my dip here, at the trough of this graph, of this curve, this is where I am balanced between my attractive and repulsive forces between these atoms, and this is going to be my most stable arrangement. And this is going to be in direct comparison to my pink situation here, where we have quite an overlap and we have quite a large amount of repulsion going on between the electron-electrons and the proton-protons, the nuclei-nuclei, etc. And so potential energy is increasing as they get closer and closer because we have so much repulsion energy going on there. It is very unstable. And then just as like a note for the general curve, the potential energy required here, this is going to be the bond energy required in order to break that bond. So if there's not much of a bond there, such as with my red instance where they are too far apart, we don't really have a bond, and therefore the energy to break it is very low. And then we have more energy required to break it as they become more stable. The unstable, we're not needing a whole heck of a lot of energy. It is kind of, we don't have to put it in order for it to break apart. It really doesn't want to be there. When we're talking about bond order, length, and strength, we will discuss as utilizing kind of like a table. Next up, we're going to be dealing with the single bond. Bond diagram that you could see here between the example atoms XX here is just 2 valence electrons being shared. You might also see a line. That's also an option, but the stacked version here is an option for what the bond diagram could look like. And this is going to be our weakest type of bond, and it is going to be our longest length between the actual nuclei of the atoms involved. This is directly compared to the double bond, where again we're going to have 4 valence electrons shared here, 4 dots stacked. This is a middle of the road level of strength, and the length is going to be slightly shorter than the single bond, but not quite the shortest. our shortest bond type is going to be that of the triple bond. And it is going to have 6 valence electrons shared between the two atoms. And it is going to be our strongest bond because we are sharing the most amount of electrons here. And it is also the shortest bond just because we had to have a larger amount of overlap of the electron cloud in order to be able to share that many electrons. So since we are sharing a grand total of 6, we had to have a greater overlap. Therefore, the bond length is shorter, and it is much more difficult to break a triple bond than it is to break a single bond. For ionic bonds, you're going to have an electrostatic attraction between your cations, which are your positively charged ions. Remember, cats have pos. Cat ions are positive, okay? And your anions, which are your negatively charged ions. And interactions between cations and anions can be explained using Coulomb's law, where we have a relationship between the overall size of the charge as well as the distance between those charges, determining how strong those bonds are. As a reminder for Coulomb's law, the larger the ion, the larger the force of attraction. So if I have a larger charge differential, I am going to have a larger force of attraction. And remember also that we are dividing by our radius squared here. So the greater the distance between the charges, the smaller the force of attraction. And that is going to be the determining factors for the strengths of ionic bonds. Continuing our conversation for intramolecular forces and potential energy, we're going to be comparing potential energy diagrams. And so we can see here 2 potential energy diagrams being represented, and we can see that the trough of this maroon line is lower than the trough of the blue line. The blue line is representing an XY bond, and it is a single bond. And we are going to have our nucleus be less attracted to the bonding electron. We have a longer bonding length, and therefore a smaller bonding energy. This is in direct comparison to the double bond that is represented by the maroon line here, where we have a deeper trough, where we have our nucleus being more attracted to the bonding electrons. We're going to have a shorter bond length, and we're going to have a larger bond energy represented by that dip in the potential energy trough there. Okay, so we are going to have to put in a lot more energy in order to break apart a double bond than a single bond. If I was to look at this problem, which states the energy required to separate ions in the magnesium hydroxide crystal lattice into individual magnesium gaseous and hydroxide gaseous ions is represented by the table below, is known as the lattice energy of the magnesium hydroxide solid. The lattice energy of strontium hydroxide is lower than that of the lattice energy of magnesium hydroxide. Explain why in terms of periodic properties and Coulomb's law. So, I don't need to actually look at the number values for the lattice energies required for strontium hydroxide and magnesium hydroxide. Strontium hydroxide involves a larger atom. That is going to be strontium. Strontium is lower on the periodic table. It is lower on the periodic table, and therefore it is going to have a larger atomic radius. That means when we're dealing with Coulomb's law, that our strontium is going to have a further distance between its nucleus and the electrons that we're dealing with. Our R value is going to be larger. Okay. So the written out reasoning that I gave was that the strontium ion is larger than the magnesium ion because it has more occupied shells. As a reminder, Coulomb's law states that the force of attraction between the cation and anion is inversely proportional to the distance between them. Since strontium is larger, the distance is greater, thus the attraction is less.